Diego is visiting this week, or he joined us Thursday and Thursday. He's going to give 2 talks while he's here about implementing cryptography. We'll talk today and a follow-up tomorrow. And he's sitting at the math department in the 6th floor, and I think he would probably be happy if people stop by and say hi, if you have some questions or want to talk about it. And
I'm in the guest office.
Yeah. And I think that's now, so what's yours? Yeah.
Thank you. Thanks for having me here. So this is a presentation from the summer school in crypto and privacy in Croatia, kind of rehashed and extended. So beware with me if there are bugs or notation flashes along the way. I did my best. So today we'll mostly talk about field arithmetic in software implementations. And then depending on how far we go, tomorrow we do scalar multiplication, or at least the state-of-the-art for scalar multiplication. And then I'll try to finish with some thoughts on post-quantum crypto lattices in particular. It's something I've been working more in recent past. So we start from like the abstract to the concrete, basic background on fields and curves. I restrict mostly to binary fields because I like them, and I think that prime fields are covered way too much. And I think this connects better with post-quantum crypto because it's polynomial arithmetic at the end. And then we do scalar multiplication, as I said, and then speed records, like the state-of-the-art based on a paper to be presented on Wednesday at SOC, where we have the fastest scalar multiplication in human history. It's a hyped claim. And then, again, we go to post-quantum. So we start very basic techniques, and then we make them more specialized by fixing the fields and fixing the parameters and so on. But first, we start from like very basic background about the area, because I don't know how much you're familiar with cryptography or cryptography engineering, which is, I would call my main field of research. So crypto engineering is basically translating theory to practice. That's the short definition, right? We worry about cryptographic systems behaving in the real world. So how can we make them efficient, robust, secure? Not only in some abstract mathematical model, but when running in software or hardware components that we know are imperfect. Of course, efficiency is very important here. It's a delicate balance between efficiency and security for all decisions a crypto engineer needs to do. Because if these implementations or crypto systems are not efficient, people won't just use them, right? Or devices won't be able to afford them. And then what's the point? So we draw improvements or techniques from basically 2 main branches. So algorithms, of course, we constantly find or look for new parameters or faster formulas or new ways to represent these algebraic structures such that you have faster arithmetic and so on. But we also draw a lot from just technological advances. Every time there is a new CPU out, all crypto engineers go to the data sheet and it's like, oh, what instructions do we get now? Can we make this useful for some crypto implementation? Do they do bit permutation? So we constantly look for new instructions, vector instructions, such that you can do this at high throughput. If you have multiple cores, how to parallelize this efficiently, and what are, again, the security impacts of this. Always favoring architectures with high arithmetic density, where it's more efficient to do arithmetic than I/O, right? Because that's the nature of crypto implementations. The focus, or at least the techniques I like the most, I get really excited about, is the interplay. When you have a new machine that has new resources, what can you do in the algorithmic terms to exploit those resources? This is when I think the area really shines. So what do we do in practice is, yeah, maybe this is, translate what the beautiful theory that the cryptographers design into something that works, right? And this is not only implementation, although I'll talk mostly about implementation here, but includes other things too, like how do you design key distribution? Where do you store keys? How do you generate keys? When you deploy this, what happens if keys leak, for example? Partial information about keys leak, and so on. So maybe more formally, that's what we do. A great thing, a great or large amount of work is in parameter search, which is a very dangerous game, in the sense that when the theoreticians think about the mathematical problems, they think about the worst case hardness, right? They pick a problem that in the worst cases seems to be hard, and then we kind of throw this through the window and pick a very specialized instance that's efficient, and we hope that the security of the two can be related in some way. This is especially true with elliptic curves. It's less true with lattices because we have these results relating average case to worst case hardness. But still, it's a dangerous game. It can go wrong. I'll give you examples, but it can go wrong in many ways. The other thing is formulating arithmetic. I mentioned this already. Like we have a certain platform with the instructions that come there. We cannot change those instructions, at least at first. If you have a processor like a RISC-V that's easy to extend, then you can create your own instructions. That's not the case in general. How can you formulate arithmetic to exploit this efficiently? We write crypto libraries, which implies also software engineering techniques, how to architecture them. I will have a few pictures about layers of arithmetic to kind of establish some contract between different levels of abstraction and implementation. How to design APIs, such that people do not misuse them and do something stupid. We do support standardization efforts by writing reference code. If you look at the NIST project for post-quantum, you see that all submissions had reference and optimized implementations of multiple architectures, which was a great change from older crypto competitions. If you look at, for example, AES, the competition, they had reference code, but this was way more prototype than post-quantum or SHA-3. So I think that's great in the long term because then future implementers can actually do their implementations based on code written by cryptographers already. I hope this will actually improve things when post-quantum translates to actual deployment. Countermeasures, I'll talk about implementation attacks and sidechain attacks later and how we can do to protect against them. I already mentioned deployment considerations, key distribution, what standards to use, what trade-offs can you have, do you employ security enclaves, is SGX broken? All of this you need to think about. And in the last few years, the area has extended to include formal verification. So instead of just building an implementation and waiting a few years such that no one breaks it, now it's trendy, and I think it makes quite a bit of sense to also formalize these implementations in some proof of system and proof properties about it, such that it's functionally equivalent to an abstract formalization of the underlying concepts, or runs in constant time, or you can derive all sorts of interesting guarantees. We publish in several venues. Chess is the main one, in the sense of where the community meets. But we have CCS, which has an applied crypto track that also receives implementation work. Real World Crypto, SAC, Latin Crypto, that's also very friendly to implementation because of how the Latin American community works. And if we get really lucky, we get an Eurocrypt paper every now and then. Sometimes an Asia Crypto one too. I assume most of you know public key crypto, so the motivating example here, because of course I'm talking about elliptic curves, is Diffie-Hellman, right? We did an efficient group instantiation with an efficient group law to do operations for key exchange, for example, for Diffie-Hellman. So one, of course, spend much time on this, but Diffie-Hellman at first started with the idea of using integers to do that, right? Problem is they're just too large. So elliptic curves came in the 80s as a way to instantiate group-based cryptography with much smaller parameters. So instead of using thousands of bits, as we have for RSA and Diffie-Hellman over prime fields, now we can use hundreds of bits. So if you can look at this, also because of the underlying problem that I will define later is assumed to be hard and exponentially hard, actually it's much easier also to compute just what's the minimum size of parameters to achieve a certain security level. So if you look at RSA or finite field arithmetic, you see that parameters quickly grow. This is security level in the sense of n-bit security, right? You need 2 to the n operations to break a crypto system instantiated using those parameters. So it grows really quickly for high security. In elliptic curve cryptography, just double the security level to get how large the group should be, right? Or the curve should be, the coordinates and the group order. So that's very convenient. Of course, it's not sufficient just to pick a group of a certain size. You need also to obey some other restrictions that I will get to define later. Because these are smaller, of course, keys are more compact, more efficient to operate with. They should be quite intuitive. So I'm already referring to an elliptic curve, so I should define it, right? So I'm using here the standard Weierstrass equation. This is the long form in which you have like 5 coefficients over some field. Here I'm not even restricting the choice of field, like some field over Q. And then we have 2 main options in practice. By substituting variables, you have prime curves on the your left-hand side there, and the short Weierstrass curve, or binary curves on the right-hand side. Both of them can be written with just two coefficients. And then there is this never-ending war between the two, which, someone finds a new technique for prime curves and establishes a new speed record, and then the binary curve people find another way, and then we keep beating each other, and that's the best way to get faster times, I guess. At least the best way we found. But that leads to tension and drama every now and then. This is a group, so of course the elements in the group are points that satisfy the curve equation, and we have a group law, right? It satisfies all the properties you expect from a group law. So it's associative, commutative, you have inverses and so on. So if you plot an elliptic curve, you probably have seen this before, over the real numbers, that's what you get, right? And the group law is, if I want to add points, I hope you can see my cursor there, it's probably easier. If you want to add points P and Q here, you trace this line, pass it from through P and Q. You know that the line intercepts the curve in another point. And then you reflect that point over the x-axis to get the result of point addition. So that's the group law. I'm writing it additively, of course, because that's how it's mathematically defined. So I'm adding points. If you want to add a point to itself, of course, that line becomes a bit special. It's now tangent to the curve at that point, right? That's the picture on the right. So you have, again, the tangent line that will pass through that point, intercept the curve at some other point that you then reflect. So if you define the group law like this, it satisfies all operations you have, or properties you need from group law. But one thing that's missing so far is there's no identity element, right? What would be a proper choice of identity element here? And you can define it with some geometric intuition by using the point at infinity. How do you define it? If you want to add a point and its negation, so point P is here, the negation of point P would be the reflection across the x-axis. So the point passing through P and minus P would be a vertical line, which doesn't intercept the curve in any concrete point. We said it intercepts the curve at infinity. So that's the point at infinity. It's the identity element for the group. So it's geometrically induced, but it's abstract, at least in affine coordinates. Please interrupt me if you have questions too. Right? But those curves I showed in the previous slide were over the reals. That's why you have continuity. So they're not good for crypto, right? The problems that we need to be secure or to be hard are not hard for those curves. So instantiate this with finite fields. And here's an example of a graphical example of a curve over a prime field. I'm picking, of course, a very small prime, 127. And then what's absolutely magical the first time you see it is that this is still a group with all the properties you expect, and that geometric interpretation of the group law still works. It's just a different choice of field now. So I have the blue points here are points that satisfy pairs of coordinates, right, x and y, that satisfy some curve equation, modulo P, right? And then if I want to add P and Q, you pass a line again over P and Q. That line now wraps mod P, which means that when it reaches 127, it goes back to 0. And at some point, it will intercept the point in the curve that after you reflect over the field, right, to negate over the field, then you get the result of point addition, just like before. So I think this is incredible. So this works for any field. We pick, again, finite fields for security. I have an example of binary field later on, such that my description is complete. So in terms of crypto, one of the main operations, again, I'm using additive notation, is what we call scalar multiplication. It's basically taking a point in the curve and multiplying by a scalar, right? Which means adding the point to itself, k minus 1 times for some integer k. So that there are k copies of p there. Of course, because these integers are large, they need to be, because they will be private keys later, right? It wouldn't be efficient to just add p to itself a number of times. We have better ways of doing this that will be described later. But given this, we can kind of encode the hardness assumption directly. If you have q and p as inputs, computing k should be hard. That's what we call the ECDLP, right? The elliptic curve discrete log problem, discrete log setting, computing exponents in the multiplicative notation or scalars there should be hard. And even if you look at ECC, this is directly encoded even in key generation, right? And for elliptic cryptography, you pick some generator, you multiply by some private key to get the public key. So even the key generation already says that, oh, if you break this, you can compute private keys from public keys, so it cannot be made secure. It's not only like being able to decrypt or to forge signatures, it's already on the key generation process. Some other definitions, we worry about when we pick curves, about the order being large enough. I'm calling the order of the curve the number of points that satisfy the curve equation to be n. We have a property called the Hasse condition that relates the size of the field to the order. That basically says that the order will be close to the size of the field, which means that if you pick a field that's large enough, you already have a point of reasonable size. So there won't be many degenerate cases to attain for. In particular, we pick n to be either prime or near prime. So there is a small cofactor such that those are the settings where the ECDLP can be made, or seems to be harder. We also have a specific class of curves called supersingular, is when the field characteristic divides that quantity t there, the trace of Frobenius, that I won't spend much time on. But it's an interesting case because they have faster arithmetic and they have a very roller coaster history in cryptography that they were proposed in the 90s. It was like, oh, this is a faster choice of parameters, we should be using that. And then Menezes and others show that they can be broken using pairings. And then they get relieved by increasing the parameters to attain for those attacks. In small characteristic in particular, they were quite efficient. And then they're broken again by Granger and others. And then they come back with supersingular isogenies, and then like Psyche is broken again. So they've been trying really hard. Let me just say that. They've been trying really hard, maybe one day. So for any point P, we also worry about the order of the point. It is a bit pointless, but we have an integer r, the order of the point that divides the curve order, Lagrange theorem, of course. And again, for security, we pick n to be large prime, right? That's the ideal case. In the curves I will explain, or I will talk about later, there will be 2 times the prime. So that's fine too. As long as you design your protocol to take care of these small subgroups, because they are a source of security problems too. So maybe to illustrate once more why this is important, why some implementation aspects are important. This is the ECDSA signature algorithm. It's just a signature generation algorithm that kind of shows how sensitive the scalar multiplication operation can be. So if you remember CDSA, you have like a hash function and some message as input and a signing key, right? This computes the signature over some group, in particular here, an elliptic curve group of points. So we start by sampling k there, that's a nonce, which is a kind of understatement because it's not just a non-repeating sequence of bits or non-repeating integer modulo the group order. Also, it needs to be made secret. It's different from a nonce in the symmetric setting. If it's ever repeated or partial information is revealed about that nonce, you can actually compute the private key. So it's a catastrophic attack against this signature scheme and other related signature schemes. But then you select that nonce k, you have some fixed generator that you multiply by the scalar k. This gives you 2 coordinates of a point, right? Rx and Ry here. And then because ECDSA is really strange, you pick the x coordinate and you then compute the signature based on the x coordinate of the point. Because the x coordinate of the point already defines the point, you have 2 choices of y for some fixed x. So it defines the point up to 1 bit. So that seems to be fine. But the point here is, or the point I'm trying to illustrate is, if that operation there, k times g, is not very carefully implemented, you leak information about k, that leaks information in its turn about the private key sk. So then it needs to be efficient and carefully implemented. Yes?
So how do you carefully implement that?
That will be the next hour. But we will do careful implementation from the field up. Yes. So I'll start from just definitions and basic techniques for, again, binary field arithmetic that are useful here, but also in other places. And then I'll make them more specialized, as I mentioned in the beginning. So you all know what a finite field is, right? It's polynomials of degree up to m with coefficients in ZP. In particular, here I care about characteristic 2, right? The binary case, because, well, intuitively, they should be more efficient on a CPU, right? CPUs are very good at processing bits. So if you represent your polynomials as coefficients, bit coefficients, that should be efficient. That's my point. And yeah, I'll present evidence that supports my claim. So I start with a very simple field that comes up in AES, just to show some of the basic operations, right? So we have some irreducible polynomial there of degree 8, which means that all field elements have 8 bits, so they fit in just 1 byte that you can represent by just concatenating the bits, right? And then if you have 2 elements A and B here, I've just picked some random polynomials in this field that can be represented in both, of course, a binary form and some hex form for easy notation. We can do operations over them. First one, of course, is addition. Addition is simple here because you just XOR these 2 representations, right? Here's a small field. It doesn't make that much of a difference just XORing 1 byte. But if you think about this machine has a 512-bit XOR instruction. So this means that if we have fields up to 512 bits, we can XOR them with just 1 instruction. And depending on how the model is, this can be computed 3 per cycle. So you can do lots and lots of additions very efficiently in comparison to integer arithmetic, right? Where you have to propagate carries and reduce. And so addition is already great for, it really comes for free in binary fields. So if we can do addition, of course, we can do multiplication too, by just doing shifted additions. So here I'm multiplying A and B. How do you do this? The simplest algorithm would be you fix operand A here, and then you scan operand B. You pick the non-zero coefficients there and their powers of Z, and you add together shifted versions of A, right? You pick A multiplied by Z squared. That means shifting to the left by 2. Add to A shifted to the left by 5, and so on. You add this together, you get a polynomial of higher degree, of course, that now you need to reduce modulo F. And then you pick F such that this operation can be done efficiently too. We have slides later on about that. So multiplication by Z is very convenient here. We just shift 1 position to the left and add F to reduce, right? I assume nothing strikingly radical so far. So why am I focusing on binary fields? Again, they show up a lot in curve-based crypto on these standardized curves. Most of them are deprecated already, but still. Post-quantum crypto, there's a list of algorithms there that use binary fields as well. Bike is perhaps the most relevant there because it's a 4th round finalist. And now that Psych is out, it's probably going to have better chance of being standardized. I have Rainbow here too, although there is a small cross because it got broken to at least the low security parameters. And not only public key crypto, but I mentioned AES, right? In block cipher design, fields are also used to define some of the building blocks. The literature has lots and lots and lots of different optimizations, and especially, well, it was already known in the 90s that in hardware, if you can synthesize the circuits in the CPUs, binary fields or binary curves in particular are more efficient than prime fields. I mentioned some of the examples why this is the case. This is also true now for software. Since around 2010 and 2019, I think for ARM, there is native support for arithmetic in those fields. So Intel has introduced instructions to do 64-bit polynomial multiplication, and ARM has a very similar instruction on ARM v8. So it's essentially everywhere.
CL is carryless multiplication.
Yes.
But what that means PIMO.
PIMO is the same thing. It's just ARM needs their own name. So, but it's carryless multiplication. You just multiply 2 64-bit integers without carries.
What stands for? Do you know?
Good question. It's not parallel. I don't remember. No, I don't think there is. Maybe packet mode, but it's not. Yeah, maybe packet mode, because you this instruction takes a 64-bit part of a 128-bit register, and then you give the index, which one you get, right? The lower or the top one, of 2 different operands. So maybe it's packed because they are packed together. That should make sense, yeah. But you know, instruction mnemonics are not really intuitive in any way. If you look at this instruction we call by CLMU is Pico Mico Duck, right? This is a very long 11-word acronym, so it's horrible. So it's getting worse and worse with these vector instructions. And in any case, now that we have similar support to binary fields than in comparison to prime fields or integer arithmetic, there's really no reason for binary fields to be slower than prime fields in software.
Are the registers large enough for the operations you want to do in practice?
So depending on the machine, right, we have from 128 to 512 bits.
Okay.
Most of this support for vector instructions, although in the case of binary fields, you don't get multiple multiplications per cycle. You can address one 64-bit field in a large register and multiply it by another indexed 64-bit field in another register. The latest, I think, is Ice Lake CPUs can do 2 or 4 of these in parallel, but we're waiting. Well, we're right now writing code to see if it's faster in practice than just doing the conventional instruction, because it has other implications, right? It's not just costs more cycles, has lower throughput, and so on. But we're trying to exploit this right now to do 4 in parallel. And then how fast that could be would be amazing. Other questions? Fine, okay. So now let's look at some generic algorithms. So I'm fixing again some generic choice of F that we get in practice to pick a trinomial or pentanomial. That basically means that there are 3 over 5 non-zero coefficients on F, such that reducing modulo F is fast. I'm representing field elements with a polynomial basis, right? So this is coefficients AI instead of a normal basis or different basis, because that's what's most efficient for software. And in software, we actually split these in words and pack them together, right? So in memory, they come as this array of AI words. That's what I will use next. So addition, we have seen is trivial, can just XOR things together. Let's look at other algorithms that are perhaps more interesting. Let's start with squaring. So squaring is quite nice in a binary field because you see there is some, it's a linear maps, there's some inherent structure there. So we fix some field element A. So squaring an element means that, well, we move each non-zero coefficient to an even position on a larger polynomial, right? So A0 stays where it was, A1 is shifted to left by 1 position, and A2 by 2 positions, and so on. In software, this actually means we are introducing zeros in between pairs of coefficients, right? We started here with the bits all packed. We just put zeros in between coefficients. This would not be efficient if you do straight bit manipulation in software, because there would be too much shifting, right? It's actually doing this in software by not using memory is tricky, because you need, as you can imagine, to shift things and sort them together, and you spend way much time than you would like to. But there are better ways of doing this. Any ideas? I'm addressing a question to the audience. Any ideas how to make this faster? By using memory. No idea, so then let's give the example. Maybe I talk about this later. We can use a table, right? So maybe we fix some bit set size, 4 bits, and then we build a table of, if we have like 4 bits, of course, this is 2 to the 4 different elements, so 16, in which we just pre-compute all of this, right? So for the 0 case, of course, the square of 4 bits, integer 0 representing 4 bits of a polynomial, the square will be just 0. We do the same for all the 16 different possibilities, right? And then on position I pick the integer that encodes these 4 bits and just put zeros and store in a table. Of course, there is a time memory trade-off here. If we pick too many bits, the table grows too large, then you suffer, right? And there will be security implications later on I will talk about too. That's one way. Another property that's very nice about squaring a binary field, we have this freshman stream, which means that you can just apply squaring linearly, so you don't deal with the pesky intermediate products here, as with integers. For multiplication, assuming that you don't have any native support to binary field multiplication, how can you do this? This technique was proposed in 2000, but still useful in microcontrollers where you don't have actual native instructions to do binary field multiplication. How can you do this? Again, you pick some bit set size, 4 bits, and then you multiply one operand b of the multiplication by all choices of these 4 bits. So again, you have a table of 16 multiplication results, right? You multiply a small polynomial by a full polynomial. And after you do that, this is online pre-computation, right, at the beginning of the algorithm. Then you can look at A as just this sequence of 4-bit sets, right? Then you can scan each 4-bit part of A, just look at the table where you have the multiplication computed, you just added this shifted. Again, works. In another way, we're using time-space trade-offs, right? We're pre-computing results that will be reused, spending memory, but that's the best we can do if there is no native support. Square roots are efficient too, and I think that's quite intuitive because if square roots are so simple, square roots should be simple too. And maybe I'll just, in the interest of time, just give the solution. So then if you look at the structure of square roots, this means that you can extract the square root of some field element by splitting the element into coefficients with even and odd positions. So we split those in two concatenated polynomials where this is the case. And then you add them together by multiplying one of them by square root of z. It's a per field constant that you can pre-compute. And again, if you can choose f, you choose f such that the square root of z is sparse as well, such that the multiplication is fast. So that will be the end. You pick the input field element, you extract the bits with even coefficients, bits with odd coefficients, you do this shifted addition to combine the two. And if f again is square root friendly, then square root of z is quite sparse, so you can do that multiplication efficiently. As you would expect, the freshman dream also applies to square roots, so you can distribute square roots without dealing with pesky intermediate values.
What was z? What is z?
Z is the base I'm using to define the polynomials, the field, yeah. I should say that I'm starting with z. When I make the choice of field concrete, I'm switching to x. Just to be confusing, yeah. Just to make sure you're paying attention. Modular reduction, I promised to also talk about, how can you reduce modulo f efficiently. So let's write f as in some form like z to the m plus a remainder, some extra non-zero coefficients. That's a reducible polynomial. How can we reduce a double size result from squaring or multiplication modulo this f? So if you get a result of, again, multiplication and squaring, you have something like this, right? The first line, right? Where you have maximum degree to be 2m minus 2. Of course, the top part here can be seen as being implicitly multiplied by z to the m, which reduced modulo f is actually r, right? So then how can you reduce? You pick the top part, multiply by r, add them together. And because there are no carries, this is actually simpler than integer arithmetic because you won't have to do this multiple times because the result doesn't grow, right? With the best choice you can have in integer arithmetic in prime fields, you have to do this 2-3 times until you make sure it's properly reduced. Because we need to multiply by this r again, that's why we pick f to be sparse. We want that multiplication to be just a few shifted additions. So we don't spend time doing a full multiplication just to reduce. That's why, again, we get so special irreducible polynomials. And finally, inversion. So there are two basic ways of computing inversion in a binary field. First one is, of course, the extended Euclidean algorithm. It's the same algorithm, but for polynomials, right? It's the same formulation. It's quite efficient, but there are problems in terms of security that I'll talk about next. I think it's literally the next slide. So to implement this in constant time, such that there is no variation of time, I will define precisely what this is a bit later. We use Itotsuji algorithm, which is basically seeing that inversion on a binary field is actually, from Fermat's legal theorem, you can see that it's powering by this exponent that you can rewrite in this way. And then you find a short addition chain to compute this power. You compute that, and for, again, proper choices of m, this is short enough that it's efficient. When I mean it's efficient, it's still a cost of like 50 multiplications. So it's the most inefficient operation on the field, but can be made practical. That's what I mean here. But if we can manage to avoid computing inversions, that's just better. Questions so far? Okay.
You were talking about when you mentioned squaring, for example, and the table solution.
Yeah.
So that is in the you have basically how to do it in software. Because in hardware it would be just a wiring.
Yes, in hardware you can just rotate, especially if you do normal basis, you just rotate things a certain number of times to compute, like 2 to the k powers. Yeah.
So these are about the software.
Yeah. Yeah, I'm restricting to software. I don't have a CPU implementing normal basis arithmetic. If we had, then we would have beaten prime curves like in the 90s, and prime curves wouldn't be a thing. That's my speculation.
Maybe I have
missed
something. Like for the squaring, why the intermediate term is missing actually?
So if you think about integers, right? When you square, you have a squared plus 2a times b plus b squared. Multiplying by 2 leads to 0 on a binary field. That's one way to see it, because you reduce modulo the field, this is just 0, right? That's why squaring distributes linearly. Another way, maybe a more efficient way to explain it is because it's Frobenius over the field. So then it should be a linear map anyways.
Okay, yeah.
That's a mathematically sophisticated explanation.
Yeah.
I also have a question.
Yeah.
So in integer multiplication, they use this fast Fourier transform based techniques for multiplication. Do those not apply to this case? Or?
They apply, but you need very large degrees for that to make sense. Yeah. So there are papers doing it. It's slightly more contrived, and you need much, much larger fields that are way beyond, I would say, even the fields we use for bike, which are on thousands of bits long. So you need very, very large fields for that to make sense. As of the state-of-the-art says, right? Of course, this could change. Other questions? Very good one. So now I explained how to do binary field arithmetic. Maybe let's try to connect this to binary curves for a bit. So now we're back to that slide with the two families, let's say, of curves, right? I care about the binary ones. In the particular case of supersingular binary curves, this can be broken, or the discrete log can be broken in quasi-polynomial time to Zhu and Granger and others, not only in theory, but also in practice. They run these large computations breaking curves with thousands of bits by using pairings in the originally destructive way. So it's dead. It's half of my PhD thesis, just dead. And I felt good deleting 20,000 lines of code. Like, so all these pair implementations just disappear. It's like, okay, this is good. In some way, yeah. It was after my defense, so I think that's fine. Like, during the defense, would be like, okay. Anyways, so we're using some substitution of variables. Of course, I won't even give intuition for that, to transform that long Weierstrass curve into a shorter curve that's easier to operate, right? To do arithmetic over. We have one particular case that is important. That's the Koblitz curve case. You might have heard of this. It's a subfield curve, also defined as a subfield curve, is when B is 1 and A is a single bit. And we'll see in a few slides down the road that there is additional structure in this curve to accelerate scalar multiplication. So I promised to have this slide. So again, I'm picking, in this case, a very small polynomial, smaller than the previous example. And then again, in blue, we have all choices of x coordinates here, the polynomials, right? And the polynomials in the y coordinate. I have in blue the pairs that satisfy the curve equation, right? The points in the curve. And again, if you do the same thing now with a line over that field, the group law is still the same. You trace a line through P and Q, reduce modulo F. This intercepts the curve in some point that you can negate the point and then find the result of point addition. A subtle detail here that you might have noticed is negating a point is different. On the integer case, negating a point is negating the y coordinate over the field. That doesn't make sense in a binary field because there's no negation, right? So actually you add x and y to negate the point. This would be the inverse, additive inverse in the curve. This is a small but important difference. So what about that group law I had in the previous slide? How can we really compute this? So then let's start with the point doubling case. I won't also give much intuition about these formulas. I'll just show them, and you can find reasons in the literature why they are like this, or you can even compute them yourself. But we have some point P that's x1 and y1 there. And then we can compute 2 times p, right? The point that corresponds to the point doubling by just computing lambda, that's the slope of the line. And then if you compute lambda that causes one inversion, you can see it there, right? Y1 divided by x1. Then you can compute x3 and y3 with just multiplications and squarings. So you invert once, you can double a point. And again, if you can compute lambda, you can see that it's quite efficient to get both x3 and y3, right? You have the option of evaluating x3 in this way or computing an additional inversion. Of course, the left-hand side is more efficient. Point addition works similarly. You have P and Q with different coordinates. You define lambda in the very natural way, slope of the line passing through P and Q. And then again, if you can compute that lambda, you can get point addition x3 and y3 efficiently too. Just multiplications and squarings over the field, and an addition with the curve coefficient A there. So this is what we call the affine coordinate model, right? We represent points by just x and y coordinates. The problem is, every time you evaluate the group law, you pay the cost of an inversion. That's too inefficient, even for the best algorithms we have for inversion. In practice, what we do is we represent points instead in projective coordinates, x, y, and z, such that there is some weighting of the z coordinates for x and y. And then this is also nice because now the point at infinity maybe can be better represented. We make it the equivalence class in which z is 0. Then you can have some arithmetic intuition maybe for the point at infinity instead of just this geometric source. In practice, we have several different choices of C and D here. So homogeneous projective is one, like both of them are 1. We have the Jacobian coordinate system 2, and the Lopez-Dahab that was very popular early 2000s and then not anymore, but it was quite relevant at some point. It was the most efficient at some point. So now the insecure way of doing scalar multiplication, we'll get there, is the double-ended algorithm. I assume you have seen this before, right? You start with some scalar, the binary expansion of that scalar, and that means that you run a loop scanning the bits from the top to the bottom. You double the accumulator every time. You add a point if the key bit is 1. And I think this is a great point to talk about. I think we'll just skip over that and see that in Koblitz curves, I talked at the beginning about parameter search, right? So actually in one of the first papers about elliptic curve cryptography from Koblitz, he already suggested this class of curves is more efficient because they are endowed with an additional map called tau, the automorphism over the curve, that can be efficiently evaluated. So if you have a point over the curve, over a Koblitz curve, and you square both coordinates, that satisfies the curve equation. And then you can rewrite the double and add scalar multiplication before to replace the doublings by applications of this tau map. And that's more efficient because it's just squarings. We saw that squarings in a binary field are really fast, right? So instead of having that complicated point doubling slope formula, now we just apply tau. And I will show you the resulting algorithm. It's the same thing. We have now we pick some scalar and we convert to some representation where this becomes an element in a ring parameterized by tau. And now we can do, instead of point doubling, we do applications of tau. And then this is a signer representation. So we either add or subtract points from the accumulator, but it computes the same thing. So it's again an example of how I pick the curve to have additional structure. And I know this further deviates from the worst case hardness of the problem to get efficiency benefits. And so far, these were not broken. So it seems to be a good idea. In practice, when the first standard for elliptic curve cryptography came up to be, they standardized several prime curves. P256 is the one probably you've used the most, even without knowing. It's the most widely deployed among the standardized curves. I have other examples of curves standardized much later. And also selection of binary curves. So the initial standards came with both Koblitz and non-Koblitz curves for several different field sizes. You probably noticed that the field sizes are interesting in comparison to the prime curves, that we have like always prime numbers. It's because this protects against one particular attack. So we picked the field to be a prime to prevent descent attacks, as it was known already at the time. And you probably, if you've been paying attention to theory and practice, you probably have heard of this curve too, curve 25519, that was standardized much later and became, a suitable candidate after it was demonstrated that it could be efficiently implemented and also more robustly implemented, as I'll claim a bit later. We also have another curve called 4Q that's super efficient. I'll be comparing against them in the final slides of the lecture. And if you invest in Bitcoin, you might have heard of this particular curve, SecP256K1, which is a prime curve with a special map. I'll be talking about this again later. But these two are more radical choices of parameters with additional structure to get efficiency. This is more conservative, but still more efficient because you can do arithmetic in a different way. All sorts of trade-offs. In terms of security, so if you read especially Bernstein's works or Curve 25519 in the paper, you see the argument that prime curves are more conservative. That's why they should be deployed widely. And I think that's just true. But the security track record of prime curves is kind of boring, right? Who needs that? We need adventure. So for binary curves, although it's not widely, but sometimes it's frequently claimed that they are broken. This is not the case. We still have instances where the discrete log is still hard, right? But if you look at long-term security, we in fact have problems. So the state of the art, for example, of breaking binary curves using quantum computer, it's more efficient. So you just need a smaller quantum computer to break binary curves in relationship to prime curves. The reason is that the gates are simpler, as they are simpler in the classical computer. So it translates almost directly. So binary curves will be broken by a quantum computer earlier. And then the second half of my PhD thesis is gone. But still, if you look at the best attacks out there, there are some attacks that work better than generic approaches for breaking the discrete log. That would be the polar row algorithm. But they only work asymptotically and they require extremely large amounts of storage. So as of now, polar row is the best attack against these field sizes. So this is still fine. In the long term, of course, this is much more risky. So, but still, because of this, binary curves were deprecated, so they're not an easy standard anymore. But I still believe that for some bleeding edge applications that don't require that much long-term security, but require efficiency now to scale properly, can benefit from this. So one particular area in which we use this particular curve and its efficient implementation was for instantiating PSI, private set intersection, because I don't think really that PSI applications need to remain secure for 30 years. They need to be efficient now, such that they can scale to billions, even billions of records. That's my claim. And now secure implementation, and I think it will be great because we'll finish around this. So now I showed one algorithm which was horribly insecure to do scalar multiplication, right? We had branches based on secret data to do operations. That's horrible. And it leaks what can be employed in a sidechain attack. Sidechain attack, instead of breaking the hardness assumption, it breaks an implementation. So it gathers leakage from the implementation to make the hardness assumption easier to break in that particular case, or just to recover the key directly. There are many different ways of exploiting that leakage. I have like a list there from less intrusive to more intrusive. The ones we care first are timing attacks, because they are easier to protect, and probably easier to exploit. If there are timing differences that leak bits of the key, you can even exploit that remotely, right? By interacting remotely with the implementation, measuring the response time, for example. But if the adversary has access to like a power source or other types of emanations, can recover the bits of the key. And in the extreme case, you can even corrupt the execution to such that it computes a wrong result that reveals bits of the key. That would be a fault injection attack. How do you defend against this? You try to make your implementations as regular as possible, such that they don't deviate depending on the bit pattern, right? You want them to look uniformly and boring from the adversary point of view. It doesn't vary too much. Or if it varies randomly, such that it doesn't leak anything other than random. How do you do this in software in the easiest way? You remove branches that depend on secret data, because, well, they leak all sorts of information from the branch predictor point of view, and from the memory access pattern point of view as well, as we'll see in the next slide. And you try to remove memory access that also depends on secret data. Why? Blame Intel. So Modern CPUs are quite tricky in how they work. They leak a lot of information in all sorts of ways. That's one example. It's called a flush and reload attack that was proposed almost a decade ago by Yuval Yago and others. After Intel introduced a user-land instruction, this means a non-privileged instruction any program can do, to evict a certain address from cache memory. So your process, you can ask the cache to evict any memory access within the address layout of that process, right? And then the problem is the following. Imagine that two different programs are linked against OpenSSL, the same library. So they share part of the address space because they're using the same library. There is a victim process doing computations, and then there is a attacker process sharing a cache and the address space. So then this attacker process can find out what the victim process is doing if the code is not written carefully. So how does it do? It evicts some address in the cache line, spends some cycles waiting, a slot we call of cycles waiting, and then it tries to read that cache line again, or that particular address. If the other process, meanwhile, use that address, this means that the read that comes later is fast, so it's a cache hit. If it's slow, it's a miss. So then that's why it's flush reload, right? So then what the adversary does is it flushes some address here, waits the gray part until it reloads again. If the victim process accesses that memory meanwhile, this will be a cache hit. It's quite short. And then, of course, the attacking process is measuring how much time it takes to read that address. If it doesn't happen, if the other process doesn't read that address meanwhile, that means that the reload will be longer. Then one process can know, oh, is this address being read or not? And that's sufficient actually to break lots of implementations. Even the double and add, I can maybe give intuition for that. If you remember the double and add scalar multiplication, if the bit of the key was 1, you add p to the accumulator, right? So this means you're reading p. So the fact that you read p reveals the bit of the key as 1. So binary algorithm is completely broken by just this simple attack. Of course, this is a probabilistic attack, so there could be an overlap between the memory access and the reload part that creates noise for the attacker. It's not an attack that you can just run once and recover all keys, but you get a noisy version of the key, or you can repeat it multiple times to recover the full secret, as you would expect.